Thank you, Julianne. Here's what I'm going to say. I'm going to say that I'm going to talk about how classical physics. I guess I should say before I read this, I don't really work in machine learning, so I'm talking about machine learning, but really I'm interested in like the structure of physical laws and then how can we use that structure to do data analysis better. I really love data analysis in all its forms, and so for me, machine learning is just one of the things in data analysis. But if you put machine learning in the title, hype and everything, might as well take advantage of it. So I'm gonna actually, a lot of what I'm going to talk about is actually intro physics, which maybe I think most people in this room probably took an intro physics class at some point. So I'm going to remind you of some things from intro physics class, and then we'll talk about how that relates to data analysis. Hopefully that will make sense. I'm going to talk about what are the kind of intro physics things that are true of all physical laws, and then how we might write a data analysis method in that form. And we're going to use the concept of invariance, like things that are invariant to coordinate transformations or whatever. And then that's going to give us better machine learning methods in some, or better data analysis methods in general. As I say, I don't care that much about machine learning per se. I more care about how we structure data analyses. And the most important collaborator here is Soledad Villar, who is a mathematician at Johns Hopkins, applied math. There's other people here, and you'll see some other names in the talk. And I have to say, it's idiotic to bring a talk about machine learning to the Flatiron Institute. I'm actually, I know way less about machine learning than many people who are in the audience, and I apologize. And you can just pay attention to the physics part of this talk or whatever. But anyway, in particular, I should call out in CCA, we have one of the best and biggest machine learning groups in the whole world in astrophysics, which is Shirley's group. And CCM has been doing a lot of innovating in machine learning. And in particular, I mentioned Rishi Kondor here because Rishi was one of the first people to, in the machine learning or in applied math world, to think about how exact symmetries could appear in machine learning. I think there's machine learning going on in all the CCs. CCQ? Yes, good. Then I think we got them all. Okay, good. Good, as I said, I don't really do machine learning, although I said that to Soledad Villar, and she said, well, you do Gaussian processes. Like, okay, fine. Gaussian processes. Actually, the weird thing is in astronomy, I'm kind of known as the go-to person for linear regression, which is a little weird to have that as my rep. But I love linear regression. I think a lot of problems can be solved with linear regression. I think people don't pay enough attention to linear regression. A lot of conceptual things are interesting about linear regression. And linear regression is often an amazing benchmark for your problem. I love linear regression. Anyway, please come and talk to me about linear regression. It pleases me more than anything. The next generalization away from linear regression would be Gaussian processes. I love them. I don't really do deep learning directly at all, but a lot of things I'm working on are on steps towards making deep learning and other kinds of high order or very parameterized methods more capable. So I am interested in deep learning, even though I don't actually do it. And by the way, at CCA and at CCM, we have collaborations on Gaussian processes. Dan Foreman-Mackey's right there, and we're one of the best places in the world right now, I think, for Gaussian processes. Good. What does the Astronomical Data Group do? The CCA isn't really organized around groups. We use an archaic language of groups, but actually there's just kind of research themes and lots of people participate in this research theme. It's not really a group. But what do we do in this research area in CCA? Lots of things. We work on hard measurement problems. We're always interested in problems where measurements are hard to make, or the data are complex, or the signals are very small. And lots of people in this room work on related things. We produce large public data sets, and even more importantly, we produce open source software. We are big supporters of open source software, and it's really important to us. And I personally am not much of a software person, but I really, really love working with software. And a lot of what we do is about software, and I love that. Of course, we do education and training and mentoring. And we do a lot of things with statistics and applied math, which will be obvious in what comes up. Good. So now it's time to go back to first year physics, which might be something, actually, saw the doctor and he said, what do you teach at NYU? And I said, physics. He's like, oh, I don't remember a single thing from my physics classes. So that's fine. I'll try to remind you of what you need to remember. So unfortunately, this isn't always taught very well in intro physics classes, but you learn about scalars and vectors in intro physics and maybe sometimes tensors if you're really there. And what is a scalar? It's often described as something that just has a magnitude, but that isn't actually sufficient. It has also transformation properties. A scalar is something that has a magnitude that's the same in all coordinate systems. It's like a coordinate-free object that has a magnitude. So like the rest mass of the electron is a scalar. Doesn't matter what frame you're in, its rest mass is always the same. Doesn't matter what orientation of your coordinate system or whatever. And then similarly, a vector is not just a list of coordinates. It is an object that has an orientation. What does it mean for something to have an orientation? It means that if you rotate the coordinate system, it transforms in a particular way. And so in that sense, a vector is a coordinate-free object. So even though you have to write down the coordinates in a coordinate system, that doesn't mean it has a meaning that transcends the coordinate system, because you could change the coordinate system and you know how it changes. So this is sort of the concept of these are coordinate-free objects. And then a tensor, I actually think a tensor is a ratio. An order 2 tensor is a ratio of 2 vectors. And then my mathematician friends are like, what? But anyway, it has something to do with relationships between vectors and so on. Good. I think I just said that. Good. Oh, I just said this controversial statement. Okay, good. So there's another thing that comes up in intro physics. Again, maybe it's not always taught all that well, but it's a really important concept. And right now, I don't think this has ever been used in machine learning, which is that physical quantities have explicit dimensions or units. So dimensions are things like length, time, mass, current, and so on. And then units are things like meters, seconds, amperes, kilograms, and so on. And these units have algebraic rules. If you divide 2 quantities, their units get divided. And if you add 2 quantities, they have to have the same units. Those are like algebraic rules. It's not an algebra, I'm told. But anyway, they're algebraic. The rules are somehow they're very, very restrictive. These rules are extremely restrictive. Most physics equations you could write down are invalid because they don't have the right units. Turns out actually, when you think about data analysis context, this is extremely restrictive, this requirement. For instance, if you want to take a transcendental function, say you want to exponentiate something or cosine of something, it has to be dimensionless. You cannot take a transcendental function of something that with dimensions. So this is extremely restriction on the laws of physics. And actually, this is so restrictive that you can often solve an intro physics problem just with the units. You don't actually have to do any. You don't even have to look up the equation. You'll find that with the given quantities, the only possible answer is the one that has the right units. So this is an extremely strict symmetry that's very important. And I would call this a symmetry. I'm going to use different language in a second. So here are the symmetries, I think, of classical physics. These are the simple, relatively simple symmetries. This is some crazy math notation I don't understand. This is a paper that we wrote about these symmetries. But the orthogonal symmetry is rotations and flips. If you take things and rotate them and flip them, you should have the same laws of physics. You can't tell whether you're seeing the universe through a mirror or directly, and you can rotate your coordinate system. Rotation is a subgroup of orthogonal. Translation that's why it's called SO, because it's the special orthogonal group, whatever. Then translations are that the laws of physics here are the same as laws of physics over here. There's super groups of that where you add them together, and I don't mean from the 80s. The Lorentz invariance is the boost invariance, like it's special relativity, like that there's a light cone and there's causal structure to the universe where things in your past light cone are always in your past light cone, even though time and space all get transformed. Anyway, that's Lorentz. Poincare is that, which and so on. And permutation, actually, the permutation symmetry is a very heavy symmetry. And this is one that is used in a lot of machine learning. The permutation symmetry is that if you swap the electrons in this room, you get the same physical system. They aren't labeled. And that's a very strong symmetry because it's combinatoric in size. It's an immense symmetry. And this is the symmetry that's encoded in graph neural networks. And by the way, the translation symmetry is encoded in convolutional layers of a convolutional neural network. Actually, the convolutional symmetry is even more restrictive than that, but it includes translation in it. Anyway, good. So these are kind of the groups that we're thinking about when we think about symmetries. And you get groups, symmetries. Each of these symmetries is associated with a group. That's what all that terminology is. I won't actually use group theory anymore in this talk. Partly because I truly don't understand it. I'm not joking when I say I don't understand it. I really don't understand it. I learned group theory in graduate school in one ear, out the other. That's why, but I have to say, one of the things I love about these kinds of projects is you collaborate with the right people and you don't have to ever learn any group theory. Anyway, so now I want to tell you something else that's kind of intro physics-y, but this is maybe a little beyond first year of physics. Way back, so general relativity, general relativity is the theory of gravity. Einstein famously created a theory of gravity published in 1915, produced it with the help of lots of friends, none of whom are on the paper, that over the period 1905 to 1915, and in that process realized that differential geometry or curved space-time was going to be important to general relativity. And in looking at curved space-time, stuff geometers had done in the 1900s, there's a book by Ricci and Levi-Cvita written in 1900 that shows that you can make objects that parallel transport on curved surfaces in a well-defined way if you always use certain kinds of notation to describe your functions or describe the relationships of these objects. And this notation is called in physics now Einstein summation notation because it wasn't invented by Einstein. And because Einstein realized after working with the geometers that if there was going to be a theory of curved space or curved space-time, it would have to be built in terms of invariants, things that are invariant in curved space-time. And so physics adopted this summation notation. And this slide has too much words on it, but basically the idea is you have pairs of objects with matched indices. And when you have matched indices, there's a summation over the indices, and then you drop the summation. And the geometers in the room will be like, but there's contravariant and covariant. Yes, I'm dropping that for this purpose, but in fact, there's an additional rule about raised and lower indices. Not important to my story, relevant to some of the experiments we did, whatever. It's just, there's a lot of technical details here. But when you learn this at some point when you take a PhD in physics, you learn this notation and you learn it under the understanding that it's like a convention that saves the number of symbols that you have to write. That's how you learn it. But that's not what it is. It is a structure for physical law. If you always write physical laws according to these rules, you will always write laws that have well-defined transformation properties in general relativity. So the general covariance of general relativity is enforced by these rules with the addition of the raised and lowered indices, which I'm not talking about because it's too inside baseball. Importantly, you can never have an index 3 times. And that sounds like a weird restriction, but you can't have a covariant object. You can't obey the symmetries if you have sums that have the wrong number of indices. Anyway, this is something that I internalized, and when I was working with my machine learning friends on some problems, I was like, well, terms like that can't exist because they don't obey the summation notation. And they were like, what? Because the two worlds hadn't collided yet. And that's one of the reasons I think it's useful to have collaborations that go across disciplines, because there are things that are common in physics that are not common in data analysis. By the way, this is an aside, but Einstein found general relativity by writing down all possible covariant expressions to some order in differential operators until he found one that had the low curvature limit of Newtonian gravity. So there's a weird sense in which general relativity was found by symbolic regression in a certain sense. He really wrote down every possible expression up to some order and found the one that was correct. By the way, physicists learned from this that what you should do is write down symmetries, put down all operators and check them all. And ever since general relativity, that's been not very useful as a direction. And but believe me, I go to many seminars a year where that is the approach. So I think we learned the wrong thing from that, but whatever. This shows that it is valuable to impose the symmetries, because if you look at all the possible second order physics you could write down in curved space-time, it's pretty daunting. But once you restrict it by that it has to be invariant in the right ways, then it's actually really tractable. In fact, Einstein, of course, did this by hand. He didn't have a computer. He did it by hand. Okay, good. Good. So why do we use machine learning in astrophysics? There's a lot of possible applications, and there's way more applications than are right here. But the kinds of things that are going on in CCA, and it's not just my group, Shirley just walked in. That's fine, Shirley's allowed to be late. Numerical simulations that we do are very expensive. There's this great hope that we might be able to emulate simulations, do them faster. What I'm most excited about is translations. You do inexpensive simulations, you do expensive simulations, and you learn the translation between them. That seems very promising to me. There's nuisances. A lot of, like, if you measure the cosmic microwave background, the cosmological parameters are encoded in this map, but almost all the information in the map is nuisance parameters. It's like almost entirely nuisance parameters. And then there's the cosmological information is hidden among the nuisance parameters. So I'm very interested in whether we could use machine learning as a way to build flexible models of nuisances, things we don't care about. And actually, this is used a lot in exoplanet work, where you're trying to find a planet in the space of stellar activity, and we don't care what the star is doing. We're just trying to find the planet. And so we model it using machine learning kind of methods. There's also high throughput data systems. Famously, Large Hadron Collider takes data at something like 10 to the 7 times the rate they can put it on disk. So they have to do fast classification. And there's astronomy projects starting now that will have similar problems. Good, but I have to say, I think that natural science is not very similar to industrial applications for machine learning. And I think a lot of people are trying to fit, there's a hammer, which is machine learning, and you say, okay, well, let's find some nails that we can hammer with a machine learning hammer. And I don't think, like, most of the uses of machine learning in industrial contexts are places where you have data, and then you have new data that you want to make predictions about that are from fundamentally the same distribution or a very similar distribution. You are literally trying to, like the customer behavior example here, you know that somebody reacted to some news story, you can predict whether the news stories they'll react to. We want human understanding, and that means a couple of things. One thing it means is that we care actually about the latent space. In machine learning, you always care about the data space, but in physics, you want to know the latent space. What are the initial conditions of the universe? What are the fundamental laws? We rarely have clean train, validate, and test situations, and we care about explanation, which, you know, a lot of machine learning explicitly rejects explanation as a goal. That's not a joke, although it's fair to laugh, but I mean, certainly in this context, like Facebook doesn't make its money by understanding its machine learning methods. They almost think it's wrong to think about it. Good. I'm very interested in regression. So again, a lot of machine learning is about classification, but I think the interesting place is regression, where you have features and you believe that data are related to features, or some data are related to some other data, or some simulations are related to other simulations. Those are structured like regressions. And then if you are looking at translators or emulators, you actually believe these symmetries apply exactly. There's no approximateness of the simulation, like if you're of the symmetry. So if you're doing a cosmological simulation, we really think the universe really is translationally and rotationally symmetric precisely. And so if we're doing an emulator or translator, we really want to be exactly translationally and rotationally symmetric. This slide is just about terminology, because I'm going to now talk about regressions, and for a little bit, just to give a sense of what we actually have done in the work we've done, which is very, very theoretical. The work I'm talking about here is very theoretical. By the way, my world is not mainly theoretical data analysis. I actually make measurements of things with actual data, but here I'm going to talk about theoretical things because I thought theoretical things might have more general interest across the CCs. And maybe you don't care about the mass of a particular exoplanet. But anyway, the idea of a regression is that you have features X, maybe tons and tons of features X, and then you have labels Y, often just one label, but often many labels. And you're trying to predict the features. You're trying to predict the labels using the features. So you're trying to find a function of the features that predicts the labels. That's the regression task. And then of course you want to apply this to new data where you have the features but you don't have the labels. So in the emulation context that I just mentioned, the features X would be like your low resolution. It would be, so let's do a simpler case. The translation case is the simplest case. In the translation case, you have a ton of low resolution simulations, which are your features, and you're trying to predict high resolution simulations, which are your labels. And that would be, and then this function h of x is a translator that translates you from the low resolution simulations to the high. Good. And so now it gets this now.
Ask a question at that point. So in my world,
you're doing it. Well
I
done.
did.
Well done, Bob.
I pressed it.
He's well trained.
It's green. So this in my world, this is only half of regression.
Yes.
This is the part that gets the expectation. How concerned are you guys about the uncertainty quantification? That is making probabilistic predictions.
Yeah, good. Bob's asking a great question. And right now, I'm just going to talk about expectations, but in fact, a lot of what we do in our group is about building like probabilistic models, even hierarchical models. We even use Stan in the group, and we really are trying to propagate error and move noise around. So we care about that a lot. One of the things that is one of the reasons I love my linear regression, like I opened with, is that I can do that uncertainty quantification very easily. As methods get more sophisticated, that gets harder. And I have kind of a whole talk about that. So for now, I'm going to punt it. But if you want to ask a more specific question in the end, I'd be happy to talk about it. In fact, a lot of what we actually in astronomy, I'm kind of known as being pretty Bayesian, which I don't really understand because I'm not particularly a Bayesian. It's just that I make people uncomfortable when I'm in the audience of their talk. So they figure I must be a Bayesian. But in fact, uncertainty is key to what we do. In fact, in physics especially, it's really, you are not permitted to publish numbers without error bars. Good. I'm a bit loose with my language. I call this symmetry. The fact that if you rotate your inputs, so you have a function, say you're predicting a vector using other vectors, so you have some positions and velocities, and you're predicting positions and velocities, well, they're all vectors. So if I rotate all the input vectors, all the output vectors have to rotate the same way. That's the symmetry. I would call that a symmetry, but the mathematicians call that an equivariance. They say that if you're varying the inputs in a certain way, you must vary the outputs in the same way. So that's why it's equivariant. And I call it a symmetry because it has to do with being coordinate free. So you can think of this as something that says that your problem's coordinate free, or you can think of it as something that says that your problem has a symmetry. It's a little subtle. And this is the mathematical language when we think about group theory. You have an operator in a group, and that operator might be a rotation matrix. And if I have an invariant function, then it says that the value of the function is the same whether the vectors or the inputs have been taken through that group operation, that rotation, say. And then equivariant is if some group operator has to happen on the output for the symmetry to be respected. That's kind of equivariant, invariant. And in some ways, invariance is just a form of equivariance, a trivial form of equivariance. I keep saying the same thing over and over again, so I think I can skip that. Okay, good. So why would it be helpful to encode equivariances? Why would it be helpful to build a data analysis system that was exactly equivariant to some symmetries that you think are happening? There's a lot of reasons. One way to think about it is that it enormously reduces the capacity of your model. So if you think in terms of linear regression, like I like to, a linear regression might be linear in a big term, like big set of monomials, like you're fitting a polynomial to something. If you fit a polynomial to something, that's like linear regression with lots and lots of terms, which are all these monomials that make up the polynomial. If you only consider the monomials that are invariant, appropriately equivariant or whatever for your problem, that enormously reduces the number of things you can write down. So it just drops huge numbers of terms. It zeroes out a huge part of your linear regression. And so the way I think about it is it reduces the capacity of your model at fixed complexity. You've just set a whole bunch of parameters to zero. And it's not dissimilar from regularization. If you do big fits with regularization, that tends to zero out or reduce the size of parameters. Here you're just explicitly doing at the front end, smack, they're all zero. And we actually find that we do way, way better if we include units as well. And we're working on that paper right now. So I'm not going to show you units results today. We're trying to get them together now. Good. One thing that I'm very interested in is that if you add these equivariances, you make your models way more robust because you know that if you're capturing something with your model, that at least you know you're capturing something that is physically realizable. If you don't apply the equivariance to your model, you don't restrict your model to be equivariant, it can explain features of your data using terms that you know must not be there. And we're very interested in adversarial attacks and understanding models in terms of adversarial attacks. And why? Because adversarial attacks reveal model inconsistencies or model non-robustness. If you can adversarially attack, if you can put in if you can take the initial conditions, rotate them and put them in and get a different answer out, you know the model's wrong. And you can think of that as a kind of attack. Yeah, good. Okay, good. So the paper I'm going to talk about, which I've already flashed you some LaTeX from, is this paper called Scalars Are Universal, which Soledad Villar led. Vishar, technically, she's Uruguayan. Good. So the idea is the setting of this problem is regression. Like I said, you have X's and Y's. Your X's are scalars, vectors, and tensors. So you have inputs that are scalars, vectors, and tensors. So your inputs to your function are coordinate-free objects, and your output is a scalar, vector, or tensor, or maybe a set of them. So that's the setting that we're talking about in this paper. And it's exactly the setting in this translator case that I said, where you have simulations, because your simulations go in with like particle masses and positions and velocities. Those are scalars, vectors, and vectors. And you get out the positions and velocities of a higher resolution simulation, which are also vectors. So this is kind of the setting we have in mind. So the story of this paper is to create the invariance. And that is, you take the inputs, which are scalars, vectors, tensors, and you contract them into scalars. So your scalars are scalars already. Your vectors, you take dot products of the vectors with themselves and each other, and that makes scalars. And you take the tensors, if they're order 2 tensors, you can contract them on themselves, or you can put vectors around them and contract them. You do all the contractions you're allowed to do with the Einstein summation rules. That produces all the scalars you can produce. And now you just make the function in terms of those scalars. So the idea is you construct the invariant quantities, and then you just do machine learning or whatever you want to do, linear regression, Gaussian process, deep learning, whatever, on the inputs that you made by making the invariants. And the thing that is so beautiful here is that you can do any nonlinear things you like with those scalars. And because they're already scalars, any nonlinear thing that you do with them, they stay scalars. And so you can make any nonlinear scalar function out of those scalars. And this paper proves I say it proves in quote, it does prove, but it's an old proof that if we're restating a known proof, which is that any scalar function of coordinate-free inputs can be written as a function of the scalars generated from the coordinate-free inputs. So this is a completely universal, and one of the things we produce, the universal in the title, we prove universality of this in this paper. That is, the mathematicians on the paper prove universality, and I go, that's nice. And then, now that was for scalar functions. If you want a scalar function of the vector and tensor inputs, you have to make the scalars, and then you can do whatever you like. Now, what if you want a vector function of the vector and tensor inputs? Then things are a little more complicated. And the way it looks is you have a set of input vectors. It turns out your output vector has to lie in the subspace spanned by the input vectors. That turns out that was something we proved. Actually, we first explained that. We have a pure mathematician on the project too, Ben Bloom-Smith, who's at NYU. And when we first said that to him, he's like, that can't be true. And he came up with a counterexample immediately. And then it turned out that counterexample only works in the SO group. But if you combine all the groups, what I said is true. The output has to be in the space spanned by the vectors that go in. So then what you do is you take scalar functions and sum them times the vectors. So you take all the scalars you can produce, you take all the vectors you can produce, and you make arbitrary scalar functions and multiply them into all the vectors you can produce, and that's your vector output. And that sounds insane, but we actually implemented. I'll show you the implementation in a second. It was very straightforward. Well, I won't exactly show you the implementation because I don't have a diagram of it, but I'll show you something. It's actually quite straightforward to do this. And again, we can prove that it's universal. So we can prove that any vector, equivariant vector function of vector, scalar, and tensor inputs can be made this way. Yeah, so here's the statement of it. So you want to get a function, which is a function of vector inputs. This is just the vector case, but you have vector inputs here, and you have a vector function that outputs a vector. You can write it as a set of scalar functions times the input vectors, and that is universal. And the reason that at first you might be like, well, that's like so complicated, but this is a very simple way of including the equivariance. There's other ways people have looked at including equivariance by using the irreducible representations of group theory or using data augmentation. Is a standard thing. People have looked at averaging over groups. People have looked at applying constraints to the optimization, and all of those methods are much more difficult than this. This is some way you can just modify an existing method. Yeah, hit me.
Will Farr would like to know, was the example that A cross B produces a new vector outside the subspace in 3D?
Oh, so cute. What a cute question. I think I say something back here? Anyway, so in the SO group, so it's true that in the SO group, you can produce something called a pseudo vector. And you can produce the pseudo vector with the Levi's theta tensor. So there's a pseudo vector in the SO group. And so which is called the cross product, and you all know it from your intro physics. V cross B is the force on QV cross B is the force on a charge in the magnetic field. But I have two comments about that. The first is that's a pseudo vector, and so actually it's only a pseudo vector output that could be produced with that thing is one thing I would say. But the other thing is actually the groups of classical physics always have parity as well, and that violates parity. So it doesn't exist in the orthogonal group. It only exists in the SO group. But even if I say, okay, you can have a pseudo vector, which I don't because it would have to be a pseudo vector, whatever. But if I do say you can have it, it's only one additional vector. So it adds exactly one vector.
Okay, a follow-up, the term equivariant isn't common in physics. Is it like covariant with dilation or something along those lines?
No, the equivariant in math is what physicists call symmetry or invariance. Like the rotational invariance or the rotational symmetry of the laws of physics is the equivariance I'm talking about. And it doesn't have anything to do with contravariant and covariant. Contravariant and covariant are about how you parallel transport in curved space-time. Now I've lost my place. Oh yeah, because I jumped through to say something about SO, but anyway. Okay, good. So I'm only going to show you a toy problem, and I agree this is a toy problem. I actually tweeted something annoyed on Twitter a few days ago where it's like, has equivariant machine learning actually been used to do anything useful? And various people tweeted back at me like papers with equivariant machine learning. Oh, I've done equivariant machine learning too, but we haven't done anything useful. We do hope to do things that are useful. Shirley does useful things, so maybe we can talk to Shirley about problems. But we did a useless problem in this paper just to demonstrate that it all works. The useless problem is this springy double pendulum, which is a classically chaotic system. If you remember, if you went on in physics long enough, you would learn that's a classically chaotic thing, and it has exponential divergence of trajectories and Lyapunov exponents. It's got fun properties. So predicting its behavior is considered hard, and so this is a kind of benchmark problem that's used in machine learning and physics, for better or worse. Anyway, we adopted it. And this was led by Wei-Chi Yao, who's a graduate student at the business school at NYU. This says we beat all the other methods that don't impose the symmetries. Yay. These are curves. This is how it works in machine learning. You show curves like this and everyone goes, yes, good, that's great, you're doing great. Actually, these are, from a physicist's perspective, these are better examples because these are showing you trajectories and how well we predict them. But I mean, to actually read the legend and understand how good that is, it's a little bit hard while I'm just racing through here. Yeah.
Do you check like Hamiltonian neural network or like
this
glass
is a
network?
Hamiltonian neural
This
network.
is Hamiltonian.
We're doing everything. So basically, we took state of the art on this problem and we just upgraded state of the art. So we could not do worse than state of the art. We had to beat state of the art. And state of the art, I think I say it in this paper. Yeah, state of the art was this paper by Finzi, and we just took his exact code and just punked it because what we're doing is so simple. We just replace the features that went into his code with invariant features. Boom, it just worked. So we didn't have to build our own neural network and choose 42 layers with hinge functions or whatever things people decide. There's some set of decisions in here. I don't know what they are. We just did exactly the same thing, but with different inputs, and we did way better. Yeah.
The springy pendulum.
She's got it.
I got
She's
it.
doing it.
The ground truth. Is that a physical springy pendulum, like, in a physics lab, or a coded springy pendulum?
Good question. Unfortunately, this is truly a toy problem.
Okay.
So there's a Hamiltonian integration that's done, I'm afraid to say, with Jack's ODE int, which I do not trust. But anyway, we're actually emulating the output of a Jack's ODE int operation. And then our problem is
In the future, I want animation of a chaotic springy pendulum, please.
Yeah. I mean, yes, these figures do. I know, and I should have had a mesmerizing thing here so that you didn't have to listen to me say all those words. You could have just stared at the springy pendulum, which is a chaotic dynamical system and really fun. Good. So, but one of the points we were making when we did this toy example was not just that we beat state of the art. It's that we could beat state of the art, but without building anything new, by just working with the existing materials. It's very easy to do this because you're basically just taking the input layer and just changing what goes into the input layer. And then we had to do some duplication of the network because we have to multiply the scalar functions by vectors back again to get vector answers, and we were predicting vectors. So we did a duplication of it and changed the inputs, and that was sufficient. And then everything else just worked. It's so beautiful, these packages like TensorFlow, JAX, and PyTorch, where you can just build your models and you have all your derivatives and you have an optimizer. It's really, really, it's an amazing world we live in. Good. Why do I keep mentioning emulators and translators? The reason that I keep mentioning emulators and translators is because they're places where the symmetries are exact. We know that the laws of physics are exactly coordinate free. Any way you view the universe, that isn't true. When we observe galaxies in the universe, or if we observe stars in the Milky Way, but let's think galaxies in the universe. The universe is homogeneous and isotropic. It's very, very precisely. Actually, back when I was younger, I wrote papers about that. But if you observe the galaxies, you don't see homogeneity because more distant galaxies appear different than closer galaxies. When nearby galaxies have, or when you look at galaxies that are nearby in space, the line of sight distance is measured in a different way than the transverse distance. And because of those noise properties, the samples don't look isotropic. It isn't exactly isotropic and homogeneous, even though the actual universe is. And so applying these equivariant methods in the real world on real data is actually a little non-trivial. Good. So one thing we're interested in, this relates a little bit to Bob's comment, a question tangentially, is what we really want to do is build models with more complex causal structure. So typically machine learning methods kind of have no causal structure. It's just like inputs in, output out, thank you. Or sorry, it's inputs in, output out, you're welcome. But that's not how we think the world works. We think there's some parts of the world we understand very well and some parts we understand very poorly. So for instance, we understand very well what goes on when we observe a galaxy. The observing of the galaxy is easy, so we have a model of that, a detailed model of that. And so you kind of want to wrap the machine learning method in something you understand, in the observing model that you understand. And then the equivariance should exist inside that latent observing model. And then the non-equivariance that comes up from the fact that you're observing along certain lines of sight and you observe things differently this way than this way can all be encompassed in that observation model. So this is the direction I think it's very exciting to go in machine learning. We have done some work trying to complexify causal structure of models, but it's early days, and I think this is really productive place for us to work. And I'm not going to talk any more about that. It's out of scope. Okay, good. So now remember when we were thinking about vectors, what did we do? We wanted to, we had to make invariants out of the vectors. So we made all the scalars we could make, and then we can do arbitrarily nonlinear things with the scalars, and they're still scalars. The same thing is true of dimensional quantities, of units. If you can collapse your dimensioned quantities, your lengths and masses and momenta and so on, into dimensionless quantities, then all of a sudden you're allowed to do arbitrary transformations of them, and you'll still be dimensionless. You cannot take the e to the something with dimensions, but you can take e to the something without dimensions. You can build a polynomial of something without dimensions. You can't build a polynomial of length, because you have length plus length squared plus length cubed, which would violate your rules. So exactly the same story is true for units and dimensional invariants as is true for these geometric invariants. You produce the invariant objects, which instead of being the scalars are now being the dimensionless quantities. And then you just build your machine learning method using the dimensionless quantities. And that is exactly what we're doing right now. And now I want to go click and show you springy double pendulum with the dimensionless things, but we're literally trying to get that to work this week. So I just don't have it. I was hoping to have it for today. I don't have it. We don't have the dimensionless form of the springy double pendulum. But one thing we found is that applying this symmetry, the symmetry that things have to be dimensionless, is extremely restrictive. We think that this reduces model capacity by more than the geometric things. And we don't quite understand why, but yeah, do it. I think, yeah.
Oh, good.
You just,
I'm failing to understand this here because it seems to me you can make everything dimensionless trivially. I mean, are you not having some extra way on how you make it dimensionless that restricts you considerably?
Yeah. No, Ari's asking a great question. You could make things dimensionless trivially in the sense that you could just take every momentum and just divide by an arbitrary thing, which is units of momentum. But no, if you think about this, the idea is, okay, so first thing I would say here is the idea here is that you have to include in your problem everything that could possibly matter physically, which is a little weird because like if you're doing a cosmology problem, you can't just put in the momenta and the positions and the masses of the particles. You have to also put in capital G. Newton's constant. And if you're doing a quantum mechanics problem, you'll also have to have h bar in there and probably c and maybe alpha. So you have
So you mean some fundamental
you have to have
dimensions.
everything that has dimensions that can matter to the problem. That all has to go in, and then you're not allowed to do anything else. So that's the idea. And the thing that's cool about this is when you do this, you can then change the units of the inputs, run your function, and you get exactly the same answer with the units changed. So it's like you literally get exactly your units. And so if you make a dimensionless identical version of your problem, you'll get identical results. But yes, but you're good. This is a good point. And in fact, when we present this to machine learning people, they often say that exact thing. They say, well, your weights just have dimensions. Like in your network, you put in things that are dimensional. Well, the weights just effectively have the dimensions, which cancel all that out. Good, but then you don't get any scaling. This means that your problem is like forced to have correct scalings. Yeah.
Emergent scales. So say, relativity doesn't have scales.
Yeah.
But clearly stars come at certain masses.
Yeah. Good. Great question. Okay, this is the question. By the way, we spent all of our time talking about this point. So there's a question about emergent scales. Like it might be that nothing, like the typical star in the universe has something, a half or something that's mass of the sun. Like there is a well-defined mass that stars tend to have, plus or minus something, that emerges from something. If we wanted to predict that, we would have to include all of the potentially relevant physics that might come into setting it. So we would need to know the temperature of the baryons at decoupling, and we'd need to know the fine structure constant and all the nuclear transitions, the nuclear transitions and all the atomic transitions, which set atomic structure or stellar structure. So like, yeah, we're not sure that this will actually help in real problems, but there are very clean problems like cosmological simulations where we do believe that like all of the emergent scales emerge very cleanly from our inputs. But that is the question. Absolutely, yeah.
Cool. I think application to use this is for when we search for equations, like stuff that Miles been doing with Kaiser. Yeah, we should do the unitless stuff.
Yes, absolutely. I'm going to talk about. I'm going to mention it at least in a moment. Yes, good. Yeah.
Probably aware that applied mathematicians have a different way of handling the dimension problem, which is to non-dimensionalize the problem first.
Yeah.
And then you're left with less parameters.
Yep.
And a bunch of stuff that's all in units of one.
Yes, exactly. Yeah.
So that's that. Then you could just apply your previous paper, and you wouldn't have to.
Absolutely.
Very
good comment.
But I don't know which is going to be better. Good. It might just be more convenient for you guys to do it your way.
So, okay, so there is a very slight conceptual difference. So it is true. What Alex said is absolutely true. That the way people like if you're I mean, I could be a little mean to mathematicians here, but a very responsible mathematician will make everything dimensionless and then solve the problem in the dimensionless state, and they're done. You're done, and we could do that, and we have done that. Here we are. There's only a very slight difference, which is there's a concept of a cost function. And if you make your problem dimensionless and you don't then propagate something into the cost function, you're effectively solving a slightly different problem. So as long as if you're thinking about transforming a machine learning problem into one that's dimensionless, you just have to make sure you get the cost function right. But yes, that also solves this problem. Good. That's a very insightful comment. Actually, that's how we got here. We were like, wait, we could just do it all dimensionless. Okay, good. So just to summarize, the kind of argument I'm making is construct invariants, do your machine learning in the space of invariants, and then put it all back together at the end. And this is very powerful for physics problems, also chemistry. There's places that people use equivariance most commonly are physics and chemistry, although I actually think there's finance problems because all the things in finance have units as well. And I think there might be a lot of other places where this could in principle come up. One thing I didn't talk about before with that list of groups is that list of groups was all for arbitrary dimensions. We had SOD, not SO3. We had OD, we had the Lorentz group in D spatial dimensions. this works at all dimensions, and most other methods for doing equivariance don't, in the sense that it gets very hard to do your group theory as your dimension gets large. Like if you have a 7-dimensional space, it's very hard to do your group theory. And we have symplectic spaces that are 6-dimensional, and this all works very simply as the dimensions go up. So it's very, this approach is very kind of scalable in the dimensional sense. It's not scalable in other senses. I'm definitely sweeping some things under the rug. Good. Shirley's point. Shirley just asked this point. We think that this will be very good for explainability, because when you are working with invariance, you have things you can explain to somebody, like what's the best feature? Oh, it's this one, which will be a dimensionless quantity. It's the Reynolds number or whatever should appear. Now, dimensionless numbers that are of interest should appear in your results. And we're very interested in this context of symbolic regression, where you could write down all, because I remember I said that the discovery of general relativity can be sort of seen like a symbolic regression. You write down all possible rules that obey your rules and then find the one that works. And in fact, in the paper we're writing, we do a tiny little symbolic regression. I mean, Miles would be ashamed by how simple our little toy is. I know. We definitely need to talk. Okay, good. Projects and questions. So the things that we're working on, and many of these things are with Kate Story-Fisher, who's over there somewhere, is cosmological applications, because cosmological applications are ones where we really think the symmetries are exact. And oh, by the way, one thing, the first time I ever interacted with statisticians years and years ago, I was a wee proto-astronomer, and I was explaining to them that we want to find the dark matter. We see the galaxies and we want to map all of the dark matter. And one of them said, that is the ultimate latent variable problem. And that stuck with me all these years, and I have no idea who said that. Good, and that's what I said. I'm done. Thank you.
Okay, so we'll take questions from the room, and occasionally I'll stop and take questions from the chat.
Recognize people myself.
Go for it.
Hi, thanks for the talk. You mentioned that there was this quote unquote trick when you want to do equivariant tensor output things. So you just build a bunch of scalars and take your input vectors and linearly combine. Is there a similar recipe for the case where your input and output dimensionality are related by like a similarity transformation, being not the same dimensions?
Good. Yes, they're good. You got that's a good question. The requirement we have, there's a requirement, and the requirement is very formal. But it's a formal requirement. It is this requirement. So if you can take a group operator in the one space and tell me what the corresponding group operator is in the other space. So the idea is like this is 7-dimensional and this is 3-dimensional. If you can tell me how the two group operators are related, you can put those two group operators there, and then we work. Then it works. But I need to know that in order to do it. Yeah.
I found it interesting when you mentioned that when doing this units-based approach, you have to include as inputs any constants that have units that are relevant.
Yeah.
Do we know all of the constants of the universe that have units? And if not, would this be used to discover new constants?
Good. Okay, so that is a great question. So first thing, do we know all the constants of the universe? It depends what area you're in. So when in cosmological simulations, we have an extremely effective model that really works very well. And so we really believe we understand all the physics in that model. But if you go to like stellar structure, which is another thing we do at CCA very well, there's some things about stellar structure that aren't fully understood and are kind of covered by effective rules. And that means we probably are missing things. Now, so that's the answer to the first part. The second part is, could we then use this to discover the existence of missing things? that is a great question. We haven't thought about that question at all yet. And I think there is a potential approach where you could include things that have unknown dimensions and learn them. And in fact, there's some, we ended up reading a lot of weird literature about dimensional analysis, and some of it is about learning the dimensions. Whereas we're assuming you know the dimensions, but you could in principle learn the dimensions of things. So I'm interested in that, but I don't have an answer for you at all. Were you gonna ask a follow-up? You look like you might. Yeah, hit it. And then I'll get you.
So one thing I remember from undergrad physics is everything is usually some parameter in my problem, or a constant of the universe, or 2 or 4, or pi, or e.
Pi, yeah. Or 4 pi to the 3rd power over 7 factorial.
Can you also impose some sort of restriction that all the numbers have to be integers or something?
Such a good idea. Yes. So that is very interesting. And we're thinking, because we did a little symbolic regression in this paper, so it made us start to think about those questions. Like, and there's some crazy numbers like 243 over 8 pi that appear in like in big general relativity expansions and so on. But we do expect a 1/2. We expect to see 1/2s and 4s before we expect to see 243s over 8 pi. So you could imagine ordering all possible like prefactors and then doing things. So yeah, I'm super interested in that. We aren't working on anything quite related to that, but some of the things going on in Shirley's group are very related to that question. And I think it is potentially very promising. Yeah.
Your example of the double pendulum, what is the goal of machine learning? Is it to predict or is it to classify? What does it do?
In this case, it is, I actually don't know which direction it is from where I am. In this case, it is, this toy example is to predict the future behavior. So you're shown the initial conditions, and as the input is the initial condition, so just basically the positions and velocities of the two masses, and then you're trying to predict this future trajectory.
How far how far?
Yeah, so in this toy problem, we just did exactly the same problem as this Finzi paper had done, because we were just showing that we could improve state of the art. In principle, you cannot predict arbitrarily far into the future because the problem is classically chaotic. So if you have even the slightest issue with either your initial conditions or your Hamiltonian description, your trajectories will diverge exponentially on a particular time scale, which is called like the Lyapunov time. So there definitely are restrictions for how well you can do in this problem. That's one of the reasons people are interested in it, because people are interested in it as a kind of hard prediction problem, but it's very much a toy. This problem is a toy. We don't consider this problem itself that interesting.
Right. So the idea is you have, instead of the dynamical system, now you have this neural network, and then you have, say, the initial condition, and where does the time come in?
Actually, this problem, this is related to something Shirley asked. In this case, the neural network itself is producing a Hamiltonian expression, and then we're doing Hamiltonian dynamics using that expression. So basically, the neural network is used to construct an expression for the mechanical energy, which is then used to integrate the system. So we're trying to learn the fundamental dynamics. So in this case, this model sort of is working in the latent space. Because the Hamiltonian isn't directly observed. What's observed is the trajectory, and you learn the Hamiltonian, which produces the trajectory.
So it's an evolution operator. And
effectively, you're learning an evolution operator, a very restrictive one that exactly obeys symplectic symmetry.
I just want to get to one question off of Zoom. We're kind of close to the end. The reception, just before people go crazy, is going to be on the roof because it's apparently 60 degrees out.
Events actually asked me, can we move the reception to the roof? It's a beautiful day.
Yeah.
And I was
okay.
like, yes, we can.
Okay, so there's a question from Reese Condor.
Reese's in the house. Hi, Reese.
Hi, Reese. It is an interesting idea to put dimensions in the sense of meters, seconds, etc., explicitly in the neural networks at the software level, a bit similar to the neural nets package that keep track of equivariant quantities explicitly, so that similar to automatic differentiation, the user can simply not mess up the equivariance accidentally. Of course, this doesn't change the expressivity of the network, but can still be very useful for physics safety.
Good. I agree with that comment.
Okay.
And by the way, Reese.
There was a question that was offered before that, which is the main result seems to be that universality of the functional form that is a linear combination of the inputs. However, the coefficients themselves are possibly complicated nonlinear functions on the inputs, right?
Yes, absolutely. Yes. Yes, that is absolutely true. So this is universality, so it's pretty complicated. So the scalar functions are arbitrarily complex. So that's why the proof of universality is actually not that interesting, because though we have a proof of universality, I'm pretty stoked, like it seems so hardcore, but in fact, you're restricted really by the expressivity of your network, not of the expressivity of functions. However, of course, if you use a Gaussian process, you get a full Hilbert space, so that's pretty cool. But I wanted to make one more comment about Reese mentioned that in the same way that there are systems that can automatically differentiate your function, there are systems that can automatically keep track of your units. And in fact, AstroPy, and Adrian is one of the authors of this part of AstroPy can explicitly keep track of your units. So one of the things and also dimensions. And so in fact, you could imagine building a package that kind of automatically does all of this in the same way that there are packages that automatically give you derivatives, which is kind of exciting. Do I have time for one more?
One more.
Good, at the back.
So I was wondering, I believe in the Hamiltonian neural networks sort of space, there are also experiments where they learn the Hamiltonian on videos of the pendulum, like little images of this thing. And I'm wondering to what extent your approach here also applies to that, given the fact that it needs to learn these vectors, and then in that case, what would they be?
Good. And now I'm trying to find something else. Oh yeah, here. Oh no, I was nearly there. Here. So those systems. So there are these famous things which you may have seen, like these systems that take a tower of blocks and try to figure out whether the tower of blocks will fall over, and they just look at video or images, and they can figure out. So they infer things about the dynamical system without actually seeing all the components of the dynamical system. Really beautiful results. The only picture, we don't have a picture for that. The closest thing we have to a picture for that would be to build explicitly the observation model. And one of the things that's very interesting that is kind of an open area of research is, could you learn the observation model and learn equivariant dynamics underneath the observation model? So you have a non-equivariant observation model, which is literally like a TV camera looking at a scene, but then you know that the scene, somehow some aspects of the scene are being controlled by a fully equivariant underlying model. That's where I want to go. That's really directly my research program. Of course, I only care about linear regression, but truly, one of the reasons I do linear regression is because I can keep the model simple enough that I can actually contemplate building such systems. That is the future.
Okay, I want to thank David for an interesting talk. Thank you everybody for your participation.